Here we have some specific exponential applications dealing with financial mathematics, which in our class we'll have a whole section on financial mathematics, but we'll kind of sprinkle it in a little bit here and there so that when we get to that section, these formulas won't be completely new. So, compound interest. This is the idea that you have, let's say, a savings account. And compound interest means the account is growing in a way that it's using that growing balance. So you make some investment, but then it's going to be this percentage growth. So the larger the account is, the more growth you're going to see. The smaller the account is, that would have smaller growth. So some pieces that will come up here is we'll have an interest rate. What we'll also have is some description of how often it compounds. So how often is that account growing? So for compounding interest, we use this A of t is equal to P, and then in parentheses, we have a 1 plus R over N, all raised to a power of N times T. So P is called the principal, and that's our initial value. It's this initial investment that we're making. R is going to be the interest rate that we're using. Again, it'll be described as a percentage, but we'll change it to percentage form. N is the number of times that the account compounds per year. So if they say something like compounded quarterly, that would be 4 times a year. If they say compounded monthly, 12 times a year. So depending on that description, that number will change. And then T is the number of years that have passed. Okay, another form is this continuously compounding interest. So like up above, they say compounded monthly, daily, hourly, but what we could have is something that says compound continuously, meaning it's always growing. And when we do that, we want to use this special form of our compound interest formula. So when it's continuous, you'll have P times E with an exponent of R times T. Call it A PERT. We have A equals PERT with RT up in that exponent. So P is the principal, R is the interest rate, T is time, so that's the same as up above. And the only thing that's different is this value E, which is a number. E is just a number. It's about equal to 2.7183. And what I did is if you check the announcement for this week, I added a little video describing what E is and where it comes from. So if you're curious more about it, it's just a short little video going over that. But the key is to know that it's just a number. So when you're typing in the calculator, you'll just use your keyboard to type in the letter E, and the calculator will know that that's actually a numerical value. Kind of like when we use the symbol pi. Pi holds that numerical value. Okay, so let's look at 2 examples here. So first we're looking at a certificate of deposit, so a CD, which is a type of savings account offered by banks, typically offering a higher interest rate in return for a fixed length of time that you'll leave your money invested. If a bank offers a 24-month CD with an annual interest rate of 1.2% compounded monthly, how much will a $1,000 investment grow over those 24 months? Okay, lots of information there. So let's grab that annual interest rate. So that's giving me R equals 0.012. We're compounding monthly, so that's telling me N is equal to 12. This is describing it as a 24-month CD, but typically T is working in years. So instead of plugging in T equals 24, I want to use T equals 2 to represent the fact that 2 years is the equivalent of 24 months. It's where you can see the relationship is how N is describing the number of times it compounds within a unit of time, and it's 12 times per year. So when we work with T, that should be in years. I guess you could adjust it to be in terms of months. If you did months, you could use t equals 24, but change n to 1. It should give the same answer. Maybe I'll double check that after I make this video, but typically we want t to be in years. All right, and then we have a $1,000 investment. So this investment is how much money we're starting the account with, and that's $1,000, and that would represent our principal. So P equals 1,000. Okay, so our function for this compounding interest account, we would have A of t equals 1,000 times 1 plus 0.012 over 12 to the 12 times t. And what we want to do is plug in t equals 2. So we're looking for A of 2, which would be 1,000 times 1 plus 0.012 over 12 to the 12 times 2. And from a calculator, we should get that that is 1,024.28. So how much will a $1,000 investment grow over those 24 months? It will grow to, so that's our balance in the account. So it's going to grow to this amount of 1,024.28. So $1,024.28. If you wanted, how much will, trying to see if they want to know the total amount or how much it grows by, because we could say it will grow by, so if you want to know the amount of interest it grew by, it would grow by $24.28, about $1 a month. Not a great account, but hey, it's something. Okay, this next one. If $1,000 is invested, so that's our principal P equals 1,000, in an account earning 10%, so R equals 0.1, compounded continuously. As soon as I see compounded continuously, I write down A equals PE to the RT, A per, because that's the formula we're going to use as soon as I see continuously. Find the value after 1 year. So we're doing t equals 1. Okay, so A equals 1,000 times E to the 0.1 times 1. And we would just type that into our calculator. And sometimes students feel like they should substitute something for E. Again, it's not a variable, it's just a number. So we would type that all in and get 1105.17. So we would have $1,105.17. So yeah, there's our two formulas. We can switch them up by like knowing how much we want the account to end up with and solve for the principal. You can solve for some different pieces here, but that's the structure of setting those up.